In this lesson, I am going to start a discussion about molecular orbital theory. Molecular orbital theory is important to understand the bonding behavior of a molecule. To learn about molecular orbital theory, we need to consider some important details. Now, when we consider electrons, electrons have both particles and wave properties. Here we consider the wave nature of the electrons because it is important to understand how the bondings are going to form in a molecule. Now let us discuss the main features of a wave to begin the lesson. Let us discuss the main parts of the wave. This is the crest, the highest point of the wave. This is the trough, the lowest point of the wave. These are the nodes. In the nodes, there are zero displacement of the particle. That means the stationary point where the wave displacement or amplitude is always zero. This is the amplitude. The height from the undisturbed, this line is undisturbed, position to the crest or trough. The wavelength is the horizontal distance between two consecutive points of the wave. Now in this diagram, the two consecutive points are taken as two nodes. This is the one node and this is another node. But we can take as two consecutive points of the crest, this point and this point, or trough. This one and the next one should be this area. Now this is the constructive interference. In these two waves are in the same phase. I have marked them as positive and negative. You can see there's the same phase on the two waves. These two waves add together and make a big, larger wave. This is called constructive interference. If you imagine now this wave is a sound wave, then resulting sound will be increased. That means we can hear loudly. If you imagine this is light wave, the resulting light will be more brighter. Similarly, if you imagine these are electrons, then the finding the electron in a given position will be high. Using these waves, we represent the probability of finding the electrons. That means the distribution of the electrons. This kind of constructive interference will result bonding molecular orbitals. In bonding molecular orbitals, the availability of electron density or electron distribution is very high. This is the destructive interference. Now these two waves are out of phase. When one is in positive phase, other one is in negative phase. In this kind of situation, two waves will cancel out. If we assume that these two waves belong to sound, then the resulting sound will be very weaker or we cannot hear it at all. If it is light waves, then resulting light will be very weak or there is no light at all. Now when we come to electrons, the finding the electron in the given position will be zero or very little. This kind of overlapping will result anti-bonding molecular orbitals. In those anti-bonding molecular orbitals, we cannot find the electrons. So bonds cannot be formed without electrons because to form bonding, electrons are need to overlap with each other. Let us discuss about the molecular orbitals. to create molecular orbitals, we have to have atomic orbitals and bonding molecular orbital and anti-bonding molecular orbital. We have to recall the things we have discussed about wave properties. Bonding molecular orbital result when two waves add together. That means they are in phase. When two waves add together, it means that the density of the electron cloud is very high. In bonding molecular orbital, the electron density is high between the two atoms. These atomic orbitals are belong to those two atoms. Those electrons are attracted by two nuclei. Then electrons are more stable and have less energy in bonding molecular orbital. So you can see with reference to the atomic orbitals, the energy of bonding molecular orbital is lower. This is the anti-bonding molecular orbital. Their energy is very high. The two waves are out of phase, so they will cancel out. The anti-bonding molecular orbital has a node between the two nuclei. Node is a region where an electron density is zero. This causes two nuclei to repel each other and make the arrangement less stable. According to this diagram, the energy for the anti-bonding molecular orbital is higher. That means they are less stable. So this is the common diagram for molecular orbital. We have to go to real example, then we can understand this theory further. Now let us consider hydrogen molecule. Before going to the hydrogen molecule, we will discuss about the hydrogen atom. Hydrogen atom has one electron that is in the first main energy level and is sub-energy level. That we can represent as 1s1. To build up molecular orbital, we have to have at least two atomic orbitals. Then those orbitals will be 1s and 1s. Those two atomic orbitals are coming from two hydrogen atoms. Then they have one electron each. We can represent in a normal way. We know now hydrogen molecule has one sigma bond. Then this would be the bonding molecular orbital. We can write sigma. And this is the anti-bonding molecular orbital. We can write that as sigma star. You know, in anti-bonding molecular orbitals, the electron density is going to be zero. Now these two unpaired electrons can form a bond. Then they should go to the bonding molecular orbital. The molecular orbital diagram of hydrogen is not that much complex. So I think you can easily understand that. Now we can go to the bond order. Bond order is very useful to get idea to check whether the given molecule is going to be stable or not. In other words, whether it is really going to be exist. The formula for the bond order is number of electrons in the bonding molecular orbital subtract number of electrons in anti-bonding molecular orbital, and the resultant value should be divided by 2. In this example, there are no electrons in the anti-bonding molecular orbital and 2 electrons are in this bonding molecular orbital. Then I am going to apply bond order for hydrogen molecule is equal half into 2 minus C. This is 1. This means hydrogen molecule is going to be stable. Now we look at helium. Helium atom, it has 2 electrons in S sub energy level. S sub energy level is in first main energy level. Then we have to consider 2 helium atoms. I am showing in this way. Each helium atom has 2 electrons in their atomic orbitals. Now these 2 electrons, this one and this one, already have coupled. Then we have to fill one of the bonding molecule orbital with 2 electrons and other one with also 2 electrons. Because we cannot separate these electrons because these are coupled. Also, helium doesn't have any other energy level. Then I am going to apply the formula. Bond order for helium is half into 2 electrons in the bonding molecule orbital and 2 electrons in anti-bonding molecule orbital. This is going to be 0. Then we can say helium molecule doesn't going to be exist. Now we consider a little bit different example that is also from helium, but 1 electron is removed. This is ion of helium molecule. Here we have to understand only 1 electron removed from 1 helium atom. Then other helium atoms would have 2 electrons and remaining helium atoms would have 1 electron. This is lack of 1 electron, that is why positive charge is there. Now when we consider these 2 electrons, they have less energy than this single uncoupled electron. We can place them in the bonding molecule orbital and the single electron can be placed in anti-bonding molecule orbital. Then I can apply the formula. The bond order for helium 2 ion is half into 2 electron and 1 electron in the anti-bonding molecule orbital. 2 is in the bonding molecule orbital and 1 is in the anti-bonding molecular orbital. This is called half as the bond order. Then we can say there is some stability for this ion. When the bond order is half, meaning low value, it means the bond is weaker, but it can exist.